start. Good morning, everyone. So it's my pleasure to introduce Michał Rams, who will talk today about IFS with random contractions.
Thank you. Okay, this will be a bit strange talk because I do not really have any theorem to prove. I will basically give some, good question. I will give basically some description of the area and things that are happening, and okay, maybe at the end there will be something that we have proven.
So this is in progress in some sense?
In a sense, yes. That is part of the results that we want to prove are not proven yet.
I see.
Okay, so what's the topic? We have an iterated function system. Last week we were talking about the situation when we have random iterated function systems where the randomness is in the translations. That is the linear contractions which are fixed, but we are adding the random translations to them.
Would be in the interval or
On the line. On the line. That was last week. Okay, so this time we are going to also look at random translations, random iterated function system given by the translations, but this time the translations are also going to have random linear part. So, for example, if we want to have maps that have only random contractions and no random translations, then we can think of something like fi of x equals ti plus lambda I x minus ti, where ti are fixed.
Ti twice,
And lambda I is lambda.
but ti plus lambda x minus ti again.
Yes, yes. This is the map which has fixed point at ti.
Ah, that's right.
But we are varying how strongly it contracts to this point. Okay, and the natural question is, okay, what do we get? So maybe the simplest possible example. We have an interval and we are doing one of the two things. One thing is that we are replacing this interval by two intervals which are 3 times shorter than the original one. And the other possibility is that we are replacing this interval by two intervals which are 4 times shorter than the original one. Now, if we are always using this construction, we are going to get the middle-third counter set with how to dimension log 2 over log 3. If we are going to use always this construction, we are going to get another counter set with how to dimension 1/2. What do we get if we are sometimes using this and sometimes using this? For example, if we are choosing them at random with probability 1/2. Each. Now, of course, there is a natural conjecture that we can immediately say that there exists some number that we will get almost surely. Yeah, this kind of ergodic situation, and it is usually so. Okay, but what is this number? And the answer is interesting because the answer is it depends.
what depends on
The Hausdorff dimension obtained almost surely in such construction. And it depends on how we are applying the randomness in this system. Let's first take the simple situation, that is, let's say that we are applying the same type of construction to every cylinder on a given level. We choose one of those with probability 1/2 each, and then we apply this construction to every cylinder we see on this level. So what do we get at level n? Of course, we are getting 2 to the power n intervals, and they are all of the same length. And this length will be 1/3 to the power of the number of times we have chosen the first time. Let's call this symbol 0, let's call this symbol 1. So it will be 1/3 to power the number of times we are choosing this construction times 1/4 times the number of times we are choosing this construction. Okay, so what is this number of times? Well, it is going to be n/2 plus minus something like O large of square root of n. Okay, so the Hausdorff dimension is going to be almost surely log 2 over the limit and then to infinity and log 2 over what do we have here? n/2 log 3 plus n/2 plus O large of square root of n. Okay, so it's going to be equal to whatever.
It's a bit strange formula.
Yes, it is correct.
On the left you have a number, to the right.
It's but limit.
Yeah.
Ah,
Oh, and this is the numerator.
Yes, and this is the numerator. You can call it as but what is it in where?
Equals S.
S minus.
S line.
Notation, yes.
It's notation.
Yes. I just want to call this number S minus. Okay, so this is kind of average between what we see here and what we see here. And here we see log 2 over log 3, here we see log 2 over log 4, and this is the harmonic average of those two numbers. Okay. And what is the other natural approach? Well, the other natural approach is, of course, that at every interval, at every level, we are doing random choice independently. Okay, so the first we apply the situation, we get two intervals which are of the same size, okay, but then in here we choose with probability 1/2, whether we are decreasing the size by the factor of 3 or by the factor of 4. And here we are also choosing independently probability 1/2, whether we are decreasing the probability, decreasing the length by the factor of 3 or by the factor of 4. So on the next stage, we will probably see intervals of different sizes.
Yes. clarify, so this is the same way as you chose last time, right?
Yes, yes. And even if not, then we can still more iteration to go on. Eventually we are going to see, well, still on level n we are going to see 2 to the power n intervals, but the length of those intervals will be widely different from each other. The length of those intervals will probably show us something like binomial distribution.
Shall I then look at your own? And maybe in the denominator, if you take this half log 3, half log 2, in brackets, then write n. And then n.
Well, yes.
Yeah, that's what it is.
Well, I don't see n denominator.
Here.
This is n. Right, big letters I don't see.
Oh, so
I
it's
thought
one.
it is 1.
No.
It's, small n.
Now it is on the screen.
Okay, I will try to write it again.
Oh, that's it, what I don't like to do.
There is also first row. Okay. So when we start taking the individual randomness, then what we get this is what Hanna did. How the dimension is going to be another number, which I will denote by S plus, and this number is given by the equation with the following equation. 1 over 3 to power s plus 1 over 4 to power s equals 1.
Could you remind what is individual randomness?
The individual randomness means that for every interval that we are obtaining in this construction, we add independently of every other interval
Even
with probability 1/2.
Even on the same level.
Even on the same level. Probability 1/2 choose one construction, probability 1/2 choose another construction. Okay, this is some number which solves this equation. I have no idea what this number is. It is not an algebraic number, I guess. And for sure, it is not equal to S minus. In fact, when you look at what are we doing here, what are we doing there, and one of those things corresponds to the logarithm of the expectation and the other expectation of the logarithm. If you want to wave your hands sufficiently. Okay, so what is going on, why it is so, which of those numbers is better, and how does it even happen? Well, let me show you a little bit of the proof of this statement. So what we have, well, at some level n, we have
Which statement are you going to? The second one.
the second. Because this one is not trivial. The second is not trivial. So we have some collection of intervals. And we want to calculate the outer dimension, and this means that we want to distribute some measure. So, of course, we want to distribute some measure which, for any interval of length L, gives us something like the length of this interval to power s, where s is not yet precise, but s is going to be this s plus. this is not really measured. Yeah? This is the measure mu n. This is the measure that we are putting on the nth level cylinders. And then on the level n plus 1, we'll have new measure, because in some of those cylinders, the children will be shorter, some of them children, some of those cylinders, the children will be longer. So the measure on the next level will be different than this measure.
Do you make previous measure finer or this is completely different?
This will be completely different.
According to this.
A new measure distributed according to this formula. Okay. But this S plus here and this formula, this is exactly the martingale formula. This S is chosen in such a way that the expectation of mu n plus 1 of C conditioned on the sigma field up to time n equals mu n of C. Okay, we have martingale, and if we know that this martingale converges, if we can apply the martingale convergence theorem, then we are going to get some measure in the limit, and this measure up to a bounded constant is going, well, almost everywhere, is going to be equivalent to the Hausdorff measure in dimension S. The measure of the cylinder will be, roughly speaking, proportional to diameter of the cylinder to power S. Okay, how are we checking this? Well, one of the initial conditions is to check that this sequence of random variables is bounded in L2. So. I mean, the expectation. What is the expectation of, let's note, xn is sum over C in the nth level sum over the cylinders in the nth level of construction of the measure, and what is the expectation of x? Or maybe, okay. Okay, so this would be the something like the sum over C1, C2 belonging to n minus first level of construction of, okay, mu n of how to write it? F1 of C1 plus mu n of F2 of C1 times mu n of F1 of C2 plus mu n of F2 of C2. What are those F1, F2? Those are those random things that restrict the interval to its left or right 1/3 or 1/4. Now, of course, this equals this, because we are getting the intervals of the equal length. So basically, what's important is the randomness. If we are with different cylinders, then those things are independent from each other. And then this expectation of this will be simply, this part is going to be 1. Because each of those is nothing, plus. But there is the part which comes from C1 equal to C2. There is this part which comes from C1 equal to C2, and then those things are not independent. Then they will give something larger than 1, of course. But this is only over exponentially small number of cylinders. Sorry, exponentially small number of pairs of cylinders. This will be only along the diagonal.
Xn is what? Is a number?
Xn is number.
So what is expectation? Oh, because it is random.
It's random.
This is
Whole construction is random.
for this random.
Yes, okay. Like x n minus 1 squared. This is the part which comes from this. And the expectation of this is simply xn. The expectation of this is simply xn. We expectation of this is simply xn minus 1. Expectation of this is simply xn minus 1. We multiply them and we are getting xn minus 1 squared plus, and the part from C1, C2 being the same, this part will be something like some lambda to power n minus 1, with lambda being smaller than 1. And so altogether this will be equal to something like the sum from n equals 0 to infinity, lambda to power n, and this one.
Sorry, don't quite understand why you have independence of C1 and C2, because it might be that they came at some point from saying
C1 and if C1 and C2 are different cylinders on level n minus 1, and what happens in one and what happens in the other is independent.
yeah, I see.
And so the expectation of the product is the product of the expectation.
Yes.
Martingale, so expectation in one and expectation in the other is simply what the measure was. So when we sum over all the possible C1s, when we sum over all the possible C2s, we are simply getting xn minus 1.
What is lambda?
Lambda is some number smaller than 1. Which
Not,
is
not 0.
no, not 0. This number describes how small part of our measure lives on the diagonal of the
So it's not exact identity, but say rhetorical or asymptotic. It
yes,
is
it's
something.
something like that. It is upper bound, doesn't matter. We just want to get the upper bound. Okay, so for this reason we have the uniform boundedness of L2, and this means that, because Martingale convectors, this means that we can construct the measure which has good geometric properties, and this gives us how to dimension S plus. This S plus is this number for which we have the Martingale. Okay. Now, of course, we can ask what happens in between. That is, we can start from this system when we have no correlations at all, and we can, in the continuous way, add the correlations to the system. There are many ways to do this. Yes, and at the end we get this situation when the complete correlation between everybody on the same level. They are all just doing the same thing. So what we are going to see as we have increasing correlation, we are going to see first the plateau.
Correlation, what's on
And this is how we increase the correlation between those random events.
So it is about this individual.
Yes. This case is when they are completely independent.
And the previous one,
This was they were completely
So
correlated.
which way do you insert this?
Well, we are doing, for example, such situation that when we have how to say it? When we have such tree, and we take the nth level cylinders, we have some constant c smaller than 1, and we are, when we are at level n, we are looking back cn times, and we are taking all those guys that have the common ancestor cn iteration back
And they
and apply them the same. Okay, so when c is sufficiently small, then we still have
So it's totally constant, yes?
yes. And we have then plateau. We still have convergence of the martingale, and this means that we still have the same dimension given by the martingale formula. But eventually we are going to get here. So from some moment on, some other thing starts to happen. We expect, of course, that this graph will be continuous, monotone, maybe smooth even, but we don't know. In fact, it is pretty difficult to understand what is the dimension of such system at the moment when the correlation are too strong are strong enough to destroy the martingale convergence. Because, of course, heuristically, we understand what's happening. In this situation, we have simply very small fluctuation. That's when we have a cylinder, and we look at the sub-cylinders of the cylinders, many iterations forward, and there are exponentially many of them. Some of them are going slightly up, some of them are going slightly down. They're going to cancel each other completely. The waves are going to be exponentially small and hence summable and hence nothing happens. But when the correlations are stronger, when they are strong enough, then we have actually unbounded waves. So we are going up, going down, we are going up, going down. And because what we are looking at is S prime, is at the martingale level, going up means multiplying by 1 plus epsilon, going down means multiplying by 1 minus epsilon. But if we multiply by 1 plus epsilon and then multiply by 1 minus epsilon, then we did not multiply by 1. We multiply by 1 minus epsilon squared, which is still smaller. So we are going to get, almost surely, exponential drift down of this sum of diameters of S plus. And this drift down means that the Hausdorff dimension drops. But how to calculate exactly how fast this drift is, we don't know. We can say that, okay, this is something smaller.
But is this theorem that there will be such plateau?
Yeah.
Exactly with this parameter c?
Yes, and we can calculate what is the endpoint of this plateau, and we can indeed prove that when we are behind this, then that's how the dimension is strictly smaller. So this we have exponential, the sum of diameter to power s is going to be exponentially smaller. But the exact formula at the moment we don't know.
And Michał, who are the we?
I forgot. We are Balazs, Barany, Antti, Kaenmaki, and me. I'm sorry.
Thank you.
Okay. So that's the situation. So maybe we can go in another direction. That was the situation when we have strong separation. And what's going on when we add some overlaps? From now on, I'm going to only speak about this complete random situation. About this martingale dimension, and this time we allow things to overlap. That is, we have simply the collection of maps. Let me write this formula again. And we do not assume that they are somehow separated in space. We do not even assume that the sum of lambdas is smaller than 1. What we do assume, well, we assume one thing. We assume that there exists some I and j such that the fixed points are different. If the fixed points are all the same, then we are simply going to get 1 point and it's not going to be interesting. We need to assume that at least 2 of those maps have different fixed points. Okay, now the question is, can we calculate the Hausdorff dimension in this situation? That is, well, of course, we are going to use some kind of transversality. In case of deterministic systems, there is a problem when we have common fixed point of 2 maps. Because for linear systems, for linear maps, having common fixed point means that the maps commute. So for linear system, having the common fixed point automatically means that the dimension drops. Dimension is not what would be given by the number of maps and the contraction ratios. It is difficult to understand what happens when the maps are not linear, but there is a very nice paper by Barany on it last year, in which he gave some example of maps, of 3 maps, non-linear maps, 2 of them having common fixed point and still having no dimension drop. Hausdorff measure was of course 0. This is band graph theorem from many years ago. But it turns out that having a common fixed point doesn't immediately imply drop of Hausdorff dimension. Okay, so what is in the random situation? Well, normally we expect the random situation to be slightly better than the deterministic situation. And it is so that is indeed we are able to prove, okay, we are able to prove under what assumption? Is now we need to assume something about randomness. That is, we need to assume that those translations, those contraction ratios, they are random and their distribution is absolutely continuous with respect to Lebesgue. Yes, if we want, okay, in fact, we need something slightly weaker, but it doesn't really change much. When we want to apply any kind of transversality argument, we really want to have things which behave like absolutely continuous distribution. Because we want to have something that intersects something in the nice way. Okay, and this is all what we need. And there is, of course, technical problem. Right? The technical problem is that in the situation when we have random translations, not random contractions, then of course this random transversality is well understood. And basically, what do we want to know? That we take a small ball, we take some point, we take some small ball around it, and we want to calculate how large measure we see in this ball. That is, we have those random guys that are being translated around randomly, and we are asking how many of them are inside this interval. Yes, we have some cylinder, and because of the randomness, its position is not exactly determined. It is somewhere all over the place, and what's the probability that it is inside our fixed interval is, roughly speaking, proportional to the length of our interval. Modulo from boundary effects, whatever. So that kind of argument, well, this is the geometric base for the arguments proving that we have indeed almost surely, for the systems with random translations, we have almost surely the Hausdorff dimension equal to minimum of 1 and the similarity dimension of the contraction ratios. Okay, so now...
Sorry, so it's not really random translations, you still have some contractions, right?
Yes, you have fixed contractions and plus random translations. Yeah, but in our situation, the problem is that, of course, as we are varying this lambda, then our random point is landing at the different positions. But if our point was pretty close to the fixed point, then those random positions will be all very close to each other. So what we will see here is not something like this, it will be something like this. And this will basically blow things up. Because it will be not true that we are going to hit this guy with this gravity. Okay, what would help us? Okay, so this is the situation. What would help us if we could somehow guarantee that we are using the points which are far away from the fixed point of the map? Because if we could say that we just need to look at the points x which are in the fixed bounded from below distance from ti, then this thing will move, okay, it will give us this constant back, of course, but constant is not a problem. And what we are going to do, we are going to do exactly that. It is, let's say that we have T1 smaller or equal than Tn. That's we number the maps in the order given by the fixed points. And of course, we assume that those fixed points are not all the same. And then what we are doing, we are looking on the symbolic sequences of the following form. Omega 1, omega n, followed by 1n, and followed by another block of symbols, followed by one n, and so on. If we take some large n, and we have some subset of the symbolic space consisting of the symbolic sequences of that form. This we are not looking on the whole random Cantor set, we are looking at some subset. And as you can see, this block, they are like repeated, and this means that it is again actually Cantor's, it is again Cantor set being an attractor of the random iterated function system. Consisting of n iteration of n maps of our random system followed by the map f1 followed by the map fn. Rinse and repeat. Okay, so what we can say about this set? Okay, so first thing, this projection of the set is in the bounded distance from the point T1. Why it is so? It is so because sometimes, like once every n plus 2 iterations, we are applying the map Fn. Somewhere the map T1, the point T1, somewhere we have the map the point Tn. We are living in this interval, but we have this map. Sometimes we are applying this map Fn. So even if we work around T1, we are going some fixed distance to the right. So this is contracting map. The contraction ratio is bounded away from 1 uniformly. So for sure, it's not a random statement, it's certain statement, but we move at least some distance to the right. Okay, but then we have n plus 1 other maps, but even if those n plus 1 other maps are all the maps f1, all the time we are trying to go back, we cannot go back to the point T1. We can only get to some point which is close, in some fixed distance. And then again we will have the map Fn which moves us away. Okay, so this means that when we look at this random Cantor set that we get from the sequences like this, they are all separate, not only those points, but also when we look at the iterations, that's when we apply some shifts to this, they are all in the bounded distance from the map, from the point T1. And this means that at all points in this set and iterations of this set, whenever we see the map F1, and we see the map F1 regularly, we have transversality. Because we are in the bounded distance from the fixed point, and being in the bounded distance of the fixed point means that the map, the randomness of the map, is really applying the corresponding translation, not only the shrinking, but it's also applying translation, which lets us apply the usual argument about transversality and get the statement about the dimension. Of course, the dimension will be smaller. But as we are taking larger and larger n, then the dimension of the expected dimension of this set is going to be arbitrarily close to the expected dimension of the full Cantor set. So that's hand-waving version of the proof.
Take small n bigger.
Yes, so we take the small n, we are taking large and large.
Big n.
No. Okay, so there is one more evil thing that we want to do. Now I can show you what is the system that was our goal. Is what the system that we wanted to.
Excuse me, sir. Could you say again, what is the conclusion?
The conclusion is that almost surely the Hausdorff dimension is given by something like that. Where S plus is this martingale exponent, and of course we can take many maps, so we can have it larger than 1, and in this case the dimension is going to be simply equal to 1.
And the lambda I are distributed in a continuous way.
Lambda, we assume that lambda i's are distributed in a continuous way. Okay, so the system that we want to play with is the following. It's like four-corner set. We start from the unit square and we take 4 maps which move our square to some rectangles in the corners of the original square, but the sizes of the rectangles are chosen at random. Okay, so as you see, when we project this to the one-dimensional situation, what we are going to see is several maps with the same fixed point. Just both this map, for this map the fixed point is this corner, for this map the fixed point is this corner, and so on. So it's exactly the one-dimensional projection is something that we already understand. Okay, what can we do about two-dimensional situation, or in general, any dimensional version of the problem? This, in general, we think about iterated functional system with random contractions given by diagonal matrices. Diagonal matrix is, of course, very, very, very special situation. But actually, there are some results about irreducible iterated functional systems, and diagonal systems have at least this nice property that they are not irreducible, that they are reducible. Okay. What is the problem? Why cannot we simply do the same thing? Well, we want to work here with the singular value potential. Yes? When we have the matrices which with the singular values alpha 1 and so on, then the singular value function is given by something like this. Okay. In case of diagonal matrices, the singular values are simply what we see on the diagonal, just put in the decreasing order. Okay. The problem is that this thing is not multiplicative. Even for diagonal matrices.
alphas are rates of contraction.
Yes, this is further diagonal.
On your picture, one rectangle is different position.
Yes, because I wanted to mention that we do not assume that the contraction in y direction is stronger than the contraction in x direction.
But still, this tension makes sense.
The potential makes sense, but this is exactly the situation when this potential is not multiplicative. This phi s of AB does not have to be equal to phi s of A times phi s of B. Smaller or equal, yes, always, but they can have to be equal. Which is a problem because we want to do the same thing, that we want to make a martingale, and to make a martingale we need multiplicative potential. Okay. But in the diagonal situation, there is one trick that we can do. That is, we can say that this phi s of A is actually the maximum of a finite number of potentials. In two-dimensional situation, it will be the maximum of two potentials, which are actually multiplicative. What are those potentials? So, phi1 s of A, it will be, let's say, s larger 1, it will be alpha x times alpha y power s minus 1, and phi 2s of A is alpha y times alpha x power s minus 1. This, we simply can fix the order in which we want to use the singular values. Doesn't matter, don't caring about whether it is decreasing order. We have at most n factorial ways of ordering them. In fact, much fewer, because as you see, plenty of exponents here are repeated, either exponent 1 or exponent 0. Doesn't matter. There is a finite number of ways we can order the direction, the axis of the coordinate system. And then we can write this formula as if that was the decreasing order. And of course, the real singular value function is the maximum of all those guys. When we change the order of singular value, then this formula can only decrease, because the exponents are in the decreasing order. Okay, at the same time, each of those guys is very nice multiplicative potential. There's no problem here. Okay, and what we can say right there, okay, let's note Wn phi s. The large sum is the sum over all nth level cylinders. Let's say we have some matrix cycle. We look at all the matrices we see on at time n, and let's calculate the sum of values of phi s of n. Okay, so what is this? This is, of course, greater equal then Wn of phi is for every I, but it is smaller or equal in the sum over I, Wn of phi is. And this means that when we calculate the zero of pressure, that is the value of S for which the exponential growth rate of this Wn is 0, it is also the zero of pressure for one of those potentials phi Si. They cannot all give exponential converging thing, because then the sum of them would also be exponential converging. Okay, so what it means? It simply means that we can choose the order of. This is actually the same thing that long time ago Krzysiek Barański did in his paper about this carpets. It's exactly the same thing. He didn't declare in which direction he has stronger contraction, either weaker contraction, and he simply said, okay, we have two formulas, and the better of them is the correct one. This is exactly the same thing that we are doing here. This is exactly the same thing that can be done in any dimension. This means that there exists I, so the P of Is equals P of phi is I. Doesn't have to be the same I for every S, of course, but that doesn't matter. We choose this S for which we have 0 of the singular value pressure, and we find some phi I for which this is also 0 of pressure. And then for this potential phi I, we are able to apply the whole argument. We can construct, we distribute the measure according to this measure phi I, check that we have exponential, that we have the convergence of the martingale, that's the L2, the martingale is L2 bounded, and basically everything works in any dimension for the diagonal situation. By the way, there is a result by Balazs and Antti saying that we have always that kind of formula. That is, for any matrix cocycle, the singular value function can be written as the maximum of finitely many, but not multiplicative, but quasi-multiplicative potentials. That is, well, basically, okay, I'm not going to present the argument. Quasi-multiplicative is almost as good as multiplicative. Quasi-multiplicative means that there exists Q and there exists K, so that for every A from sigma n and for every B from sigma m, there exists C from sigma k, such that phi of ACD is greater or equal than Q phi of A phi of B. And from above, we assume that we have simply submultiplicativity, and from below, we have something like this, that it is not true that when we have two matrices and take the potential of the product of the matrices, then it is something large. No, it can be something very small, but you can put something between A and B, which is very small. This is the product of not many not many how it's called, generators of the cycle. And it's good enough to put those matrices in such position that now the potential on them behaves in the correct way.
So here you have inequality only in one direction.
But in the other direction, we assume phi of AB smaller or equal than phi of A phi of B.
This would be sufficient to use martingale argument.
In this case, though, I think not. This is no martingale. There are some fluctuations of n level. And I guess we have no control about how those fluctuations gather. Okay, anyway, so that's more or less what I know.
Questions, comments?
Online.
Oh. Just
Yes, please. Someone have a question? Oh, I have some question. So I am interested in a very simple situation when we have say a shift and a Weber's transformation with two fixed points, one expanding, one attracting, and what is it in understanding what will be the attractant situation, and is it kind of
For the one map,
for two maps? You have just two maps.
what of the type?
One of them is a shift and the other is a Weber's.
Okay. Shift is parabolic, yes?
Yeah.
On the line.
I guess this would be something like modular group, yes? I would have to get in. Maybe even more complicated.
So it's not something trivial.
Even cocycles of two matrices are not together. Two by two matrices. Yes, Karol, you wanted to?
I would like to ask a question related to this one-dimensional situation. When I think it is on the left-hand side, blackboard maybe, when you just change the contraction ratio uniformly, probably. So you add the multiplicative error maybe to the left if possible. On the left bottom, the left top corner. Am I right? Did I understand well, Michał, that in every step when you apply, you add a random multiplicative error to lambda I? Am I right?
Yes, lambda i's are random, chosen from some absolutely continuous distribution.
Yes, and you do it in a way that it's always independent. So when you are on level n, then still this multiplicative error is different for all at all nodes when you are at level n. Am I understand? Yeah. So we did something related, not this, with Perez and Solomiak, but we had the same error on level n. So for every level n, and something came out. So it's most probably it's different. The result should be different, I guess.
That would be this other case. That would be this case when we have full correlation on the level.
Yes, exactly. This is what we did with Pere, and then the result is different, of course.
Yes, this is not the martingale situation. Yes.
Yes. Okay. Thank you.
Any other questions? From mine? Okay, if no more questions, so let's thank Michał again.